kinematic example problems, you should have the slides presentation shared with you, so you should be able to follow along there. Certainly, if you'd like to jot down the problems first or print this up, feel free to. As of right now, at least when I'm recording this, this is the first set of example problems I've done. So a couple things about when I do example problems. First off, I recommend that you follow along. Heck, even try to go ahead and set up the problem and then unpause the video and see if your setup was correct. Then, once you've done that, I recommend pausing again before you punch it into a calculator, and then you can unpause the video, check your answer, and see if you can figure out if you're right or what you did wrong if you weren't. I also recommend keeping your formula page handy as we go through these. And of course, if you have any questions as you go, jot them down, and when you come back to class, ask me them, of course, or get a hold of me some other way. Anyway, we're just going to dive right in here. So we're asked, what is the velocity? Anytime I'm doing a problem, I try to label the parts. And since we're asked what here, I'm going to go ahead and put a question mark there. I will say if the problem's in a textbook, I'm not going to take the time to rewrite the problem, but what I do on my page usually is I will sit there and I will write out the different values that I'm given. Anyway, what is the velocity of a car that travels 335 meters? That is a distance. The notes may have used d for distance. I'm trying to get into the habit of using the more formal x and y, and that's because we'll do a lot of things like this on a Cartesian graph, and so then we use those for our distances. As a side note, I know that this is a distance because of its units. You really need to use your units to get familiar with, okay, when I have a value given to me here, if it doesn't say it travels a distance of 335 meters, you have to be able to identify that this is a distance, and you're going to use your units to do that. In 30 seconds, of course, 30 seconds is going to be a time. So we need a formula that has those three in it, and I happen to know the velocity formula is velocity is equal to distance divided by time. If you want to be picky, it's a change in distance over a change in time, but since we're just given values and we're not measuring those, then we can leave off the change in. And also, to be honest, frequently, we start measuring from 0 and 0, so then rarely will we need the change in. If there is a change in, then it is always final minus initial, and that's because if you start at 0 and go to 335, if you were to use this first, then you'd end up with a negative number when you did the subtraction here. And so then, because velocity is a vector, the direction matters. And so to have the number come out positive, because traveling forward we call positive, we have to have final first. And so anytime you have a change in a delta, it is always final minus initial. Anyway, plugging our values in here then, x is 335. Meters, make sure you keep your units with you. I'll show you why here in just a second, and time is 30 seconds. So punch that into a calculator, which I've done previously, and you can see here I get 11.6 repeating. And then for my units, I'm going to check those right here, and I'm going to do the math with the units also. So I have meters per divided by second. That's going to give me meters divided by second as my units here. And so then I know that this I did this right because my meters per second is what I expect a velocity to come out to. Early on, when these are formulas that you saw probably way back in algebra, if not pre-algebra, this is going to seem pointless. Later on in the year, though, when we get to using some weird units or some combined units, you're absolutely going to want to be doing this. It's called dimensional analysis, and it's a quick and easy way to check your answer, because if your units come out properly, then you know you probably plugged the terms in properly and identified them properly. Anyway, repeating here is bad, and we have to consider sig figs. So this one here has 1, 2, 3, 4 digits. These zeros are significant because they wouldn't have been written if they weren't. In this particular case, they're not placeholders because there's a number before the decimal and they come after. So 4 sig figs there, only 1, 2, 3 here, and so then because of that, we need our final answer to have 3. This repeating bar means that there's not actually 3, so we're going to round that off to 11 point. I think that number is wrong. Sorry, it was 11.16 repeating, and so then anyway, rounding that off to 2 sig figs, 11.2 meters per second. I know that was wrong because I have recorded this video now, I think 3 times, trying to get a good take. Anyway, moving on to the next one. What is the acceleration of a car? So A equals question mark. That travels 76 centimeters. That's going to be a distance and gets up to 3 meters per second. That's a velocity in 1.5 seconds. That's a time. All right, I want to solve for acceleration. So I look at my formula page for a formula that has acceleration, and it turns out that this one here has it. A couple others do as well, but this one here is the shortest of them, so it's the one I would personally choose. Or you can just remember that acceleration is change in velocity divided by change in time. As a side note, that's not what this one looks like, but when we derive these, I pointed out that final minus initial is the change in, and this is just a rearrangement of it. So anyway, acceleration, change in velocity divided by change in time, which means I have extra information. I'm not going to need that distance there, but plugging these values in, 3 meters per second. When I go to do sig figs, I'm going to put those zeros back in, but there's no problem leaving them off here. Divide by 1.5 seconds, and I'm going to get 2 for my answer there. We also have to do the math with the units, and just to prove to you the acceleration units here real quick, meters per second divided by seconds is the same thing as saying meters per second divided by seconds that way. Of course, anytime you're dividing with fractions, we take this one and we flip it and multiply instead, and so then we have that, and then when we multiply meters times 1, we get meters, and when we multiply seconds by seconds, we get seconds squared. So that is meters per second squared. I need to bring in sig figs here, so we have 4 there, 3 there, and only 2 there. So my final answer needs to have 2. Even though this came out exact, to show my sig figs, I'm going to take the time to write that 0. Otherwise, if I were to need this to use this value in a future problem, my sig figs would be off because I didn't have this one proper. So we're going to go with that. Moving on, how far? That's going to be a distance. Does an apple fall? Oh, vertical distance. So I'm going to change that to a y. From a tree, if it takes 0.95 seconds, that's a time for it to fall to the ground. What is the final velocity as well? So 2 different questions here that we're solving for. And I'm going to use the distance and free fall equation. So that is y sub ff is equal to 1/2 times g times t squared. Now, you don't need to memorize these formulas, but you will note that that formula is not here on this formula page. It's just kind of hidden. It's right here inside of this kinematic equation. Well, what's that other stuff? Well, this is an initial position. Certainly, if we wanted to consider the top of the tree to be a height, we could plug in an initial position there, and then we could see how far it fell. But we're going to consider the top of the tree to be 0, or at least where the apple was to be 0, and so then we can just measure the distance as an absolute value as it goes down. Initial speed, I'm assuming that if it's falling from the tree that it was at rest to begin with. The problem probably should have explicitly stated that, but that's going to be 0. 0 times time is going to give me 0, and then I have 1/2 at squared. Well, g, the acceleration due to gravity, is just a special a, so 1/2 at squared here. This is the same formula. When I go to punch this in the calculator, I don't like working with fractions, so I always turn my 1/2s into 0.5. So 0.5 times 9.81, that is meters per second squared. The time here, when I punch into the calculator, even though powers come first, I always lock things like this in with parentheses. So 0.95 seconds. And the other reason I do this as well is because putting the squared outside the parentheses reminds me not only to square the number there, but also to square the seconds there. So you'll notice, oh, I didn't use the parentheses that time, but you can see I have it punched in here all in one line, and I highly recommend that because if you make a typo, it's as simple as going back up there, grabbing that one line, and fixing it rather than having to retype the whole thing. And if you do it over multiple steps, that's what you're going to have to do. Anyway, I'm not going to jot that whole thing down. Only 2 sig figs there on our one value that we're given, so our final answer is going to have 2 sig figs, so that's going to be 4.4. And as a side note, meters per second here, or excuse me, meters per second squared there. Here we square not only the time, we also square the seconds, so we end up with seconds squared there. Should be obvious that those 2 cancel out and we get meters, which makes sense for a distance. Our second question here, what is its final velocity? Velocity final is equal to, we have this formula here. This formula page uses x and x naught. This would be final and initial. So I tend to think of this one as final because it's just how I learned it. But anyway, that formula is Vx, or Vi, excuse me, initial plus a times t. So then it had no initial velocity, so that would be a 0 meters per second plus a times t. That's special case of acceleration due to gravity, so 9.81 meters per second squared. Time here is 0.95 seconds. So then we cancel out the seconds with the Sorry, I got off the page there. Screen there. Seconds times the second squared. That's going to give me meters per second for my units. And then I got to find where this one is on my calculator. I failed to do it originally. There we go. It is 9.3195. Again, we only want 2 sig figs for my final answer, so I'm going to go 9.3 meters per second is equal to velocity final. If you wanted the average velocity, it's literally just average this with the starting velocity, and you would have the average velocity it traveled, which you could also use then to calculate the distance. You could use average velocity instead of factoring in the acceleration, the fact that it has a changing velocity. Moving over here, a airplane accelerates down a runway, so that's an acceleration for that amount of time until it finally lifts off the ground. Determine the distance it travels. So this is going to be our long kinematic equation again. When you look at the formula page and look for formulas that have those values, use those values. So there was no initial distance, there was no initial velocity, so those two terms are going to drop out. Rather than plugging in zeros this time, I am going to just skip using them. So I'm just going to jump straight into 0.5 times acceleration 3.20 meters per second squared multiplied by the 32.8 seconds squared. And so now x is equal to, I've got to find this one again. There we go. It's that one there. And so then I get that number there, 1721. 0.344, and that would again come out to be meters for our distance. Sig figs, we have 3 and 3, so our final answer needs to have 3, so that's going to be 172, but this is 1,721. If I write this is 172, so that doesn't work. So I have to put the 0 in there, but that 0 is insignificant because it's not being locked in with a decimal. So this final answer does have 3 sig figs, but you can't just get rid of these zeros. I've had students try to do that, and you're literally changing the number. So you can't do that because 172 meters is way too short for that airplane to take off. So there you have it. Next car starts at rest. Oh, that's an initial velocity of 0 meters per second and accelerates uniformly over a time. They didn't give us an acceleration there. Over a time of 5.2 seconds for a distance of 110 meters. X determine, here we go. Determine the acceleration of the car. So that's why we don't need that one. So I think we're going to use this one here. We have an initial velocity, acceleration. No, there's no distance in this one. This one needs final velocity. This is our long kinematic equation again. X is equal to x naught plus v naught t plus 1/2 a t squared. The difference is this time I have a distance, and then we have no initial distance, no initial velocity. Well, we do have initial velocity. We're told it's 0 this time. So then 1/2 times a times t squared. So there we have it. This time we're solving for a. Well, this is just rearranging it with basic algebra. And so then I'm comfortable just taking this and rearranging it as is. So like I said, I usually plug in 0.5 here. So then I'm going to have 110 meters divided by 0.5 times 5.21 seconds squared. If you would rather do the 0.5 multiplied by the square of that first and then do the division, of course that's totally okay. The other thing is the 1/2 there. I could have, instead of doing this, I could have taken that, and to get rid of it I could have flipped it, and I could have done 2 times 110 in the numerator divided by the 5.21 seconds squared. And like I said, if you wanted to combine these first and then do the division, of course that's okay. Anyway, this one then, you'll notice and totally by accident, though this is something that I just pointed out, I typed this in wrong the first time. Because I did it all in one step, I could just go up, hit enter here, it recreated that line, and then I was able to edit it and change that 100 to a 110, and I ended up with 8.1. In terms of sig figs, 3 here, that's not locked in with the decimal, so that's only 2 there. So we're going to leave this one at 2 sig figs, and that one does stay a 1. And then again, unit-wise, let's see here. We have meters divided by seconds squared, so that makes sense for an acceleration. Yay. We're only going to do one more problem. I know there's 2 here. I'm going to try to delete this slide for future, but it turns out that this one asks 2 parts, and the second part here gets into using the formula that you would have used here anyway. So I'm going to just do this one as an example for both of those. Anyway, a race car accelerates uniformly from 18.5 meters per second, that's a velocity initial, to 6.1 meters per second, that's a velocity final, in 2.47 seconds. Determine the acceleration of the car and the distance traveled. So we want to know A, and we want to know X. Now, you probably could pick which of these 2 to solve for, but I'm going to go with just the first one it asked for, and then we'll work out the second one. So for this one, we're just going to use the acceleration formula. Again, it's just a rearrangement of this formula here, but acceleration is equal to change in velocity over change in time, which is velocity final minus velocity initial over time. And so then it's just plugging in these values, 46.1 minus 18.5. I forgot to do my units there, so I'm going to do meters per second on the outside, just factor that out. And then the time is 2.47 seconds, and then again, all in one line here, punch into the calculator, I get 111.17, 3 sig figs, 3 sig figs, 3 sig figs. I'm going to round this one off to 3, 111.2, and that's going to be meters per second squared again. Then we want to know the distance traveled. So we need a formula that has distance in it. Well, this one, of course, has distance in it, but it only has initial velocity, and our initial velocity was 0. I think we could use this one here, but I want to show you how to use this formula since we haven't used this one yet. And this one is useful when you're not given a time. And again, we are given a time there, but I'm going to use this one to solve for it, just so you see what this equation looks like. If you want to take a stab at this one, again, this would be the same formula if we're solving it. If you want to do one where you're not actually given the time and absolutely have to use that formula. Anyway, that formula is velocity final squared is equal to velocity initial squared plus 2. This particular version shows x minus x, but really that's just a change in x, delta x, and since we just want to know the total distance it's traveled, and I'm assuming that it started at 0 and went some unknown distance that we're solving for, that it's okay to just call that x or delta x. So that's going to be that. Then plugging the values in, 46.1 meters per second squared is equal to 18.5 meters per second squared plus 2 times the acceleration. We're not given the acceleration up here, but we just solved for it. So 11.2 meters per second squared times x, which is what we want to solve for. Now, I will point out here that when I go to punch this into the calculator, I'm not going to use a rounded value. I'm going to use my prior answer, the unrounded value. I won't penalize you if you do it the other way, but it's going to work out the close enough, and to be honest with sig figs, it shouldn't matter, but I'll give you credit for both. Anyway, on this one here, I'm trying to find out my calculator here. I've done so many of these. I took it step at a time this time. Anyway, that one became 2125.21. This one is 342.25 plus I did those two, and again I used my old answer there, and I get 22.3. I'm going to round it off here, but again, when I go to use it again, I'm going to do that, and that's meters per second squared. I didn't include them in here, but this would be meters squared per second squared, as with this one here, meters squared per second squared. We're then going to move this over here, and we're going to do that by subtracting, so then I get 17.832.96 meters squared per second squared is equal to 22.3 meters per second squared times x. Divide both sides by that 23, and I end up with x is equal to 79.8 79.7809 repeating. Sig fig, again, we want to have 3, so that's going to become 79.8. And meters squared per second squared divided by meters per second squared. You'll hopefully notice that obviously the seconds cancel out and the meter and the denominator cancels out with the squared, and we're left with just meters, which makes sense for a distance. Anyway, that is it. Be sure to let me know if you have any questions.